In the last lesson, we were finishing our discussion on email, and we closed out with a thorough inspection of POP3, IMAP, and HTTP mail. Now it's time to move on to lesson 8 of our course on networks and distributed systems. This section is on the application layer, and the course is based on the book Computer Networking, a Top-Down Approach by Jim Couros and Keith Ross. So let's proceed. We've grown accustomed to accessing information on the web by entering some sort of web name into the URL. By the way, URL stands for Uniform Resource Locator. Names like Amazon.com, Netflix.com, Gmail.com are popular web names that most of us know very well. However, the underlying network technology communicates exclusively with numbers, specifically binary numbers, zeros and ones. For a human being to communicate using binary numbers would be almost impossible. At best, we might use a decimal equivalent of a binary number. For example, we've already discussed the fact that every host on the internet must have a unique ID. That ID is normally represented by 4 octets of binary numbers, which translate to 4 decimal numbers separated by dots. An example would be an Amazon IP address, 254.239.26.128. Or a Netflix IP address, 52.32.190.154. Now imagine how difficult it would be to communicate over the internet that we've grown so fond of if we had to remember numbers like those. Most of us don't do so well with long numbers at all, even phone numbers sometimes. So a system has been developed using people-friendly names like Amazon.com. That's much easier to remember than that decimal IP address that I gave you a few minutes ago. We need a directory service that translates host names like Amazon.com to IP addresses. This is the main task of the Internet's domain name system, open paren, DNS, close paren. The DNS is a distributed database implemented in a hierarchy of DNS servers and an application layer protocol that allows hosts to query those distributed databases. The DNS servers are often Unix machines running the Berkeley Internet Domain Name software. It's usually abbreviated BIND, B-I-N-D. The DNS protocol runs over UDP and uses port 53. There we go, those ports again. Port 53 is the port used for the UDP packets for DNS. DNS is commonly employed by other application layer protocols, including HTTP, SMTP, and FTP, to translate user-supplied host names to IP addresses. As an example, consider what happens when an HTTP client, the web browser, running on some user's hosts, requests the URL www.yourschool.edu/index.html. Yourschool.edu is the domain name. In order for the user's host to be able to send an HTTP request message to the web server www.someschool.edu, the user's host must first obtain the IP address of www.someschool.edu, because the computer, you understand, the underlying network technology, knows nothing about that name, www.someschool.edu. This is done as follows. Number one, the user machine runs the client side of the DNS application. Number two, the browser extracts the host name, www.someschool.edu, from the URL and passes the host name to the client side of the DNS application. Number three, the DNS client sends a query containing the host name to a DNS server. Number four, the DNS client eventually receives a reply, which includes the IP address for that host. Number five, once the browser receives the IP address from DNS, it can initiate a TCP connection to the HTTP server process located at port 80 at that IP address. This string of events happens every time the user inputs a domain name in that URL. Think about that for a second. You type in www.someschool.edu and you usually get an immediate response, correct? But the fact of the matter is, before you got that response, that series of steps had to take place for your client to even get the IP address to send that query to. So it's really kind of amazing, don't you think? DNS adds an additional delay to the internet applications that use it. What much of a delay was it? How often do you think you have to wait long before you get a response from that website? Fortunately, the desired IP address is often cached in a nearby DNS server, which helps to reduce DNS network traffic as well as the average DNS delay. Now, essentially what that's saying is that there are multiple DNS servers out there. And so when your client sends out a request, one of those servers is going to pick it up. A host with a complicated host name can have one or more alias names. Alias host names, when present, are typically easier to remember. Like HTTP, FTP, and SMTP, a lot of TPs in there, the DNS protocol is an application layer protocol since it runs between communicating end systems using the client-server paradigm and relies on an underlying end-to-end transport protocol to transfer DNS messages between communicating end systems. In another sense, however, the role of the DNS is quite different from web file transfer and email applications. Unlike these applications, the DNS is not an application with which the user directly interacts. Instead, the DNS provides a core internet function for translating host names to their underlying IP addresses for users' applications and other software on the internet. We see that much of the complexity in the internet architecture is located at the edges of the network. The DNS, which implements critical name-to-address translation process using clients and servers located at the edge of the network, is another example of design. DNS is also used to perform load distribution among replicated servers, such as replicated web servers. Busy sites like CNN.com are replicated over multiple servers, with each server running on a different end system and each having a different IP address. For replicated web servers, a set of addresses is thus associated with one host name. The DNS database contains this set of IP addresses. When clients make a DNS query for a name mapped to a set of addresses, the server responds with the entire set of IP addresses, but rotates the ordering of the addresses within each reply. Because a client typically sends its HTTP request to the IP address that is listed first in the set, DNS rotation distributes the traffic among replicated servers. DNS rotation is also used for email so that multiple mail servers can have the same alias name. Suppose that some application running in a user's host needs to translate a host name to an IP address. The application will invoke the client side of DNS, specifically the host name that needs to be translated. DNS in the user's host then takes over, sending a query message into the network. All DNS query and reply messages are sent within UDP datagrams to port 53. Note, they used UDP and not TCP. After a delay ranging from milliseconds to seconds, DNS in the user's host receives a DNS reply that provides the desired mapping. This mapping is then passed to the invoking application. DNS is complex, consisting of a large number of DNS servers distributed all around the globe, as well as an application layer protocol that specifies how DNS servers and querying hosts communicate. Regarding that DNS using UDP datagrams, not TCP datagrams, UDP datagrams. Recall that the TCP guarantees service and UDP does not. It's the large number of DNS servers that explains why. One of those servers is bound to get that datagram, so guaranteed service is not necessary. If not, then the host link is probably dead and it will get a message that the site cannot be found. In other words, when your software on your client machine sends out that UDP query, it's going out the internet and it is spreading around the globe through all the connections until it hits the first DNS server it sees. And if it misses one, it will hit another one. That's why the guaranteed delivery is not necessary. Several things to consider. If a simple design used only one DNS server, then any number of problems could arise. There would be a single point of failure. If the DNS server crashes, so does the entire internet. A single DNS server would have to handle all DNS queries for all of the HTTP requests and email messages generated from hundreds of millions of hosts. Can you imagine? A single DNS server cannot be close to all of the querying clients. So if there were only one, it might be halfway around the world and probably travel along some possibly slow or congested links. This can lead to significant delays. The single DNS server would have to keep records of all the single DNS server would have to keep records of all of the internet hosts. Not only would this centralized database be huge, but it would have to be updated frequently to account for every new host. A centralized database in a single DNS server simply doesn't scale. Consequently, the DNS is distributed by design. In fact, the DNS is a great example of how a distributed database can be implemented in the internet. Well, there's some important information right there, folks, so why don't we stop here so that you can examine it more closely, check your notes, take care of any assignments that you may have, and come on back. Well, we're going to continue on some more on DNS.